Sir, 2 weeks online FDP on electric vehicle application, control, and smart charging using artificial intelligence. Today, our guest speaker is Dr. Varsha Shah, madam. I welcome you, madam. It's my great pleasure to introduce Dr. Shah, ma'am. Dr. Shah, ma'am, working as a professor in SVNIT Surat College, Engineering College. Ma'am has total 1.5 years industrial experience. Also, she has 32 years of teaching and research experience. Madam has strong research interest in hybrid and electric vehicles, energy source and management applications. Today, Madam will deliver the speech on role of soft computing techniques for energy management of hybrid electric vehicle. I request Madam to start with her session.
Okay, thank you, and good morning to all. Okay, let me just. Madam, I have to start my presentation, right?
Yes, Madam.
So I think you has been already logged in.
Uh, there
No,
were problem
there
with my mic.
there is no, I think, options available for me to start presentation.
Uh,
Uh, I'm not getting any
okay,
option for my presentation. Now, okay, now I
okay,
am
okay, Madam.
now. Yeah. So once again, good morning to all. Today I will deliver my talk on energy management system for hybrid electric vehicle. Hello, I am audible.
Yes, Madam, you are audible.
Screen is also visible.
Yes, Madam.
Okay. I'm sure that all of you are very much familiar with the uh, electric vehicle and their components. So in a short way, I will start that. So usually why we need electric vehicle or basically a hybrid electric vehicle. Electric vehicle is you can say uh, the way or it is a group in which one of the can say the series of a vehicle will be defined as a hybrid electric vehicle. And as we all know that the adverse environmental impact uh, due to overuse of the fossil fuel, which will turn in terms of the global warming and acid rain, then again depleting oil reserves, and especially transportation has the major dependency on the fossil fuel, and driving source for majority of vehicles is usually IC engine, and we know that IC engine will always work with very low efficiency. One of the reason behind this, the IC engine low efficiency operation, is there is a single source which we are using to operate vehicle under different mode of operation. That means your vehicle is operating either in little bit steady state mode and transient mode. And in this case, the only single device will provide power to the vehicle. and during acceleration mode, the vehicle demands very high power, but in a normal mode operation it is always reduced by 5, divide by 5 or divide by 5. That much amount of the power is needed for the normal operations, and that's why we are not able to operate this engine with its full capacity. That is another reason. That's why it has a low efficiency. Of course, it requires higher maintenance, cumbersome control. These are the main disadvantage. If you will compare it with the electrical propulsion system, then we are using electric motor along with the controllable power source, which we call that as electric drive. So higher power to weight ratio, good control, and it is environmentally clean, operate with very good efficiency compared to the IC engine. And the main another advantage that we are getting by using electrical propulsion system in a vehicle is a regenerative braking, because we know that when the vehicle is running on a road, it gain lots of momentum. That momentum is available in terms of the stored energy in the rotating part. So when you break the vehicle, lots of energy we are only wasting as a heat. So that can be recovered, and that process, what we call it, is a regenerative energy. And we know that the motor can operate as a generator. So single machine can be either used as a motor or generator. Then equivalent range, cost, and safety of conventional vehicle while reducing fuel cost and harmful emissions without compromising on performance of vehicle. Of course, as far as the cost is concerned, maybe higher, it is towards higher side, but the operating cost of this electric vehicle is very, very less. Of course, there are certain hurdles uh, still not allowing the complete penetration of electrical vehicle, especially on Indian roads, because people are always very much familiar with the all luxuries that what we have with the conventional vehicle. So this HEV configurations basically in two, can say, two part. Either it has a series architecture or a parallel architecture. So when we talk about series architecture, all the component of the vehicle will be connected in series. And when we talk about HEV hybrid electric vehicle, it is combination of the conventional engine along with the electrical propulsion system. So mechanical plus electrical propulsion systems are used to drive the vehicle. So we'll have here, you will have the engine. Engine will be connected with the generator. So engine will run the generator. Generator will generate appropriate charge, and that will be passed on to the battery. And then that has been given to the converter, and converter will drive the motor. So you might have this, you can say the charger may charge your battery or may charge your flywheel, and battery is supplying power to the electric motor. But in this particular case, all component will have the same similar size, and that is, I can say, the disadvantage of series architecture. So usually series architecture is preferred for a very high capacity uh, transportation system, that means in a bus, truck, where they can use it. And in case of parallel architecture, the engine and motor both are connected in parallel. They are propelling, sorry, either the electric motor will propel the vehicle or engine will propel the vehicle, or both in a combination they may propel the vehicle. So in this particular case, the size of engine will greatly reduce compared to the series configuration. And then we have other advanced configurations or architectures, maybe a combination of series, parallel, etc. Again, this HEV configuration will have the either you have the pre-transmission parallel HEV configurations or post-transmission parallel HEV configuration, in which the gearbox will be after the motor and engine will be connected to the common torque coupler, or in post transmission the engine will be provided earlier in gearbox. And as we know that the motor can be controlled very easily compared to the control of engine. and then it has been given to the torque coupler, and then it pass on to the wheel. So basically the HEV component will be IC engine, then motor will be driven by the energy storage device, and this whole system, motor and energy storage system, will be provided with the power electronics devices as well as appropriate control circuit. Similar way, the IC engine will also provided with appropriate control unit, and then you will have the mechanical power transmission unit, and then that is with the gear and clutch, and finally the movement will be passed on to the wheel of a vehicle. In case of energy storage device, we'll have the options battery and supercapacitor. So battery can work or act as a primary source, and supercapacitor is act as a secondary source, depending on the requirement of vehicle functionality. So what type of energy storage system that we need for the vehicle applications? The one is high energy density for driving range, high power density for acceleration. As I have told you that, just give me a 1 minute time. I'm just connecting a board. Hello.
Yes, madam.
Sorry, because it takes a little bit more time. So the energy storage which we need must have the high energy density, high power density for acceleration, and this is for the driving range, and capacity to absorb power during regenerative braking. It means that usually if you look at the profile of the vehicle operations, if I'm just mentioning the speed profile, especially in the city, then this is nothing but the speed versus time graph. And if you'll see that this period is a transient mode of this, and here on this side the variation in speed is very small, so we can say it is a normal mode operation of the vehicle, and this is nothing but we can say a braking mode operation. So your vehicle is operating in different modes, is operated in different modes, and that's why the power requirement will vary. So for a driving range, to cover a specific driving range, it must have the high energy density to support the acceleration rate with respect to the highest speed, with respect to highest speed, and the time corresponding to your reaching to highest speed from t is equal to 0 to some say t is equal to t1. So that always required what should be the power density of your weak energy storage system. Capacity to absorb power during regenerative braking, that is again related with this acceleration. We call this as the deceleration part or the braking part. So braking and acceleration is a transient, and the remaining portion we call usually interpret as a normal operation. So we need to have the trade-off between the power density and energy density becomes important for vehicle applications. Variation of power density with SOC and charge discharge can be very important, because your system must be able to deliver high amount of power during acceleration part, and it must have a very high cycle life, because cycle life will be defined as charge and discharge of your battery. So if it is high, then the life of your vehicle will be larger, and it requires the replacement cost for the battery will be greatly reduced. It must have the high coulombic efficiency, low cost, and low operating temperature. So this is our requirement. But the convention, or you can say the available electrical vehicle in market, they all are operated with the battery. So we'll have certain limitations for EV batteries. As I have told you, that vehicle impose variant driving conditions which demands variable power from the source, average, and the peak power. And that's why the primary energy storage usually we prefer to have the battery, but battery will have poor efficiency, as we all know, low power density, short life cycle, low operating range, and low current capability are the main limitations of battery. So battery are not designed to provide a burst of power over many hundreds or thousands of the cycle, that is during acceleration and deceleration performance. Even in urban drive, due to repeated acceleration and deceleration, the degradation of the battery will be high, because here we are talking about only single source battery has to provide this. And as we know that, as I already told you, that during acceleration, let's say it requires 10 kilowatt of power, then definitely during normal mode operation, it requires very small amount of power, 2 to 3 kilowatt of power. So if you look at this, if I'm just designing my battery with 10 kilowatt, and I'm simply utilizing 2 to 3 kilowatt of power for most of the time, and this 10 kilowatt I'm utilizing only for the short period of time, then definitely the size of battery increases and the overall efficiency of battery reduces, because I'm not using it with its full capacity. So these are the certain limitations related with the battery and a single source. And that's why we need to have a source. Another, or we can say the requirement is like that the source must have high power density and high energy density. But none of the source available in market will have the high energy density and high power density. So what we need is we have to find out, or we have to design our EV battery in such a way that it offers good amount of power density and energy density. People are working in that, and based on that, the conclusion is that we may connect one more energy storage device will have a high power density, so that the requirement of vehicle power requirement will fulfill. So the another device on which people are focusing, that is known as a supercapacitor, ultracapacitor. It is also known as a electric double layer capacitor, which is you can say functionality is like a normal capacitor, but as the name given ultra indicate that it has a very high amount of capacitance. Capacitance current capability is very, very large. It can charge and discharge at any level, and you can charge it and discharge it very fast. So, like in case of a battery cannot charge or discharge with any rate of current. The supercapacitor can charge or discharge at any rate of current. So if you will look at the definition of supercapacitor, can be defined as energy storage device that stored energy electrostatically by polarizing an electrolyte solution. Unlike battery, there is no chemical reaction when the energy is being stored or discharged, and so the supercapacitor can go through hundred or thousands of charging and discharging cycle with no degradation. That is not the case with the battery. So supercapacitor use an electrode having a high specific surface area. As the surface area of electrode is very, very large, it can penetrate more number of electrolytes, and that's why it offers a very high value of capacitance. And this area is created by the porous carbon electrodes with a small charge separation that is of the length 10 angstrom and thinner dielectrics. In this figure, what I have shown you is the supercapacitors are available. Like the battery, we say that the batteries are a battery unit is built with the number of cells. Similar way, this big figure, this are nothing but the modules of the supercapacitor, which is built with the supercapacitor cells, which I have shown here in this figure with the small. It means that like a battery, we have the supercapacitor cell, and supercapacitor will have the voltage is of 2.7 volt. People are still focusing to increase the cell voltage of supercapacitor from 2.7 to a larger value, and they might have reached up to 4 to 5 volt, but not more than that. So this is the only limitation of supercapacitor. Otherwise, it has a capacitance value in terms of can say you can start with zero point 0.1 Faraday to 3000 to 5000 Faraday. Even the people have reported that the supercapacitors are available in with the value of 30,000 Faraday also. But available market availability is with 3000 to 5000. The charge gets stored in supercapacitor physically on electrodes with the and this way and provide considerably high power density, as it is a very normal that the positive electrode attract the negative ions and negative electrodes gather the positive ion, and that way the physically the charge will be accumulated on electrodes, and that's why they provide high power density. There is no chemical reaction take place on the electrodes. Ultracapacitor tends to have a long cycle life, but absence of any chemical reactions also makes them to a low energy density. So this will be a supercapacitor is defined as high power density, low energy density. Battery is defined with high energy density and low power density. But the another advantage that what we are getting with the supercapacitor is internal resistance is very, very low compared to battery. So making it highly efficient, but it also cause a high output current if the charge at a state of extremely low SOC. The reason is that the SOC of a supercapacitor is directly proportional to the terminal voltage of supercapacitor. And as we know that the any storage device will always identify with that state of charge, and if the state of charge is directly related with the terminal voltage of supercapacitor, indicating that when you are absorbing a power from the supercapacitor, then the SOC reduces, and as SOC reduces, the terminal voltage will also reduce. So if you will start your battery to charge from the low value of SOC, then definitely draw a higher current to raise its voltage from this small value to a larger value. So initially it requires high current. The high pulse power, so a supercapacitor will be now identified as a high pulse power capability based on ultra low internal resistance, wide operating temperature range, that is between -42 to +65, minimal maintenance, relatively high power abuse tolerance to overcharge and over temperature. This is the most important thing, which is not the case with the battery, that you cannot overcharge your battery or you cannot operate above the certain range of temperature. So this is possible with the supercapacitor. It has a fast transient response, high cycling capability. The cycling capability is in terms of 1 lakhs. You can charge and discharge it for a 1 lakhs times or even more than that. That has been mentioned, 1 million charge discharge events at 75% state of charge swing. That means when the state of charge will change from 00 to 75%, indicating that your system has reached to, sorry, this is not in terms of state of charge, but it can be in terms of the energy or the power. So when you will have the 100% charge SOC, sorry, supercapacitor, and if you discharge it, at that time 100% charge, the voltage is, let's say, 2.7 volt, the full voltage. And when you discharge it, and when it reaches to the 50% level of its SOC, then the energy available in the SOC will get utilized by 75%, and at the same time the voltage is also 2.7 by 2 volt. It means that the voltage will get reduced to half the voltage, which is corresponding to SOC to be, sorry, SOC to be 50%. The energy, available energy from supercapacitor has been discharged, corresponding to 75%. So only remaining is only 25% energy is left in the system. So this is a very emerging, rapidly emerging and increasingly applied technology. Supercapacitors are used in different places, not only for the vehicle, but even for the electric power system also they are preferred, are capable of storing and discharging energy very quickly and effectively. Only the limitations, that is 2.7 volt, but it has a very high current capability. And as it is double layer, you can see here that this is the positive electrodes, this is the negative electrodes, where the charge, negative charge, here you'll have the positive charge, negative and positive charge. So the double layer will be formed at each electrodes, and they offer the two capacitance like they are connected in series. These are the two capacitors offered by these two electrodes connected in series, and this is nothing but, you can say, the electrolyte or internally whatever you will have between these two electrodes. They will offer that resistance, and certain resistance offered by the electrodes, and other you can say connected resistance, wire connectivity resistance. So now to match with the power requirement, power and energy requirement of EV, we need to have battery and supercapacitor to be used in parallel. So, what are the reasons for battery supercapacitor hybridization? So, one is to match with high specific power, with high specific energy. Higher energy efficiency of the battery can be achieved, because now when we are using supercapacitor, let's say your system is demanding 10 kilowatt of power. This is the maximum power. And let's say the 2 kilowatt of power, that is for the normal operation. Then this is the rating of supercapacitor, and this is the rating of your battery. So you can see that if I do not have the supercapacitor, then my battery capacity should be of 10 kilowatt, but now it has reduced to 2 kilowatt. So the battery performance will be much better, and battery operate with higher efficiency, and the, you can say, the charge discharge cycle will greatly reduce, because all peak charges will be supplied and absorbed by the supercapacitor, which you can charge and discharge at any rate and any number of time. Again, you will get effective regenerative braking is possible, because if you allow only battery, then super and capacitor is not there, then this braking energy has to be dumped into batteries, and again the battery capability will be a question mark in terms of the current at the time of regenerative braking. So now we are dumping that power in the UC, and that's why the effective regenerative braking is possible, and that will improve the battery life, and smaller battery pack is required. So that's why now we go with the hybridization of the source, so that you can fulfill the requirement of vehicle. So usually that can say the energy storage device will be always identified through the Ragan plot in terms of their specific power and specific energy. So if you see, the specific energy is higher for the battery, even higher for the fuel cell, while the specific energy for the supercapacitor is smaller, but the specific power will be larger. So it is now residing between the normal capacitor and battery. Supercapacitor is residing. So now if we look at the electric vehicle, the complete electrical vehicle, this is, I have shown the simulation model. If you want, because before we go for the prototype of electric vehicle, we always go with the simulation mode model. We always first perform the simulation and then go with this. Then here the question is that, let's say we will have the energy storage system. Of course, here I have not shown the engine part. In the next slide I will show you that. I'm just showing you the electrical propulsion part only of HEV. So we go with the multiple energy storage system or a single energy storage system that we have to determine. Then this energy storage will be interfaced with the inverter through DC to DC converter, so that you can regulate the current and voltage level of both the, or you can say, the multiple energy storage devices. Then you will have the motor controller, which is provided with the motor and inverter. Now, to determine that what should be the size of your motor, what should be the size of our capacitor, DC to DC converter, and energy storage device, we need to find out the driving of mode operation of the vehicle, which we are usually defined with the drive cycle, and then how much power the vehicle is demanding when it is running on road, that we identify through the vehicle dynamics. So once we know the vehicle dynamics of vehicle, we can get the information about the power requirement, torque requirement of vehicle at the wheel of the vehicle. So these things we are simulating through a known driving pattern. We have the known driving pattern, and through the known driving pattern we find out the power and torque requirement of the vehicle. And usually for that, I will show you in the rest of the slide that what are the power that the vehicle is demanding. Usually it is rolling resistance power, that is referred to the wheel, which is moving on a road, so it stretches the surface of the road. So this rolling resistance will come in picture. Other is the vehicle is running on a road and it is always operating maybe in opposing or the in the supportive direction of the wind. So we have the wind power loss, and the vehicle will get accelerated from zero speed to some normal speed, or may get, let's say it is working here and now again we would like to accelerate it. So this acceleration power that is also demanded by vehicle, of course for the duration of this acceleration power will be for a short period of time. So the third power is accelerating power, and the fourth power is that when the vehicle is moving on road, then whether his road is a flat road or a inclined load, whether it is with the inclination or not. So these are the four forces which are acting on the vehicle. So from the known drive cycles, we can calculate that. And then accordingly, we will size the motor, we size the inverter, we size the DC to DC converter, and we size the energy storage system. And once we'll have that sizing, then here the question is that, well, see, we are moving in these directions, and then we are finding this, and here finally the motor will drive the wheels of a vehicle. Now this multiple storage unit, if we have multiple storage unit, then we need to have the energy management unit which will manage the power flow between the two sources under different mode of operation of vehicle. And otherwise this DC to DC converter and the motor will be equipped with their own controller. And now to synchronize operation of the each and every compartment of vehicle, you need to have the master controller. And this master controller will see or check the status of each and every compartment of the vehicle, and accordingly it provides command to the individual elements of a vehicle to drive it. So now here, when we would like to find the sizing of this, we usually go with the efficiency model. That means I know the efficiency of motor, I know the efficiency of inverter, DC to DC converter. I can finally find that once I know that, okay, this is the power demanded by the this wheel, which we are calculating through this. And then after we know the efficiency of motor, we know the efficiency of the other units, we call it as a transmitting unit or a mechanical structure for the power transmission. So we have to consider, sorry, that can be here placed over here, and I have already mentioned with this transmission system. So we have to consider the efficiency of the transmission system also. So the power available at wheel we are calculating through this. So usually you can now input over here also, and then from the wheel we just move in the reverse direction. That means we consider what is the efficiency of transmission unit. So once we know the power at wheel, we can find the power at transmission unit. Then to this motor to driver, means everything will be calculated based on their efficiency model. And then finally we'll come with the conclusion that what should be the size of your energy storage device in terms of their power rating. So how that can be implemented? Uh, So before that, you just look at that, the power flow diagram during propulsion of the forward wheel drive vehicle. That means only two wheels, forward two wheels are connected with this propulsion device, while the rear wheel will be operated through the transmitting and differential unit. So you will have, this is nothing but the wheel, and the power needed to the wheel will be supplied from battery. And let's say we have the hybrid source, battery and supercapacitor we are using, through bidirectional converter and the logic to select the energy source, and the, can say, the other control algorithm uh, to operate this DC to DC converter. And then finally we'll get uh, required amount of power in terms of, you can say, the voltage and current at this point, and then it has been passed on to the inverter. Then we'll have the inverter control logic, as well as we have the motor control logic also. And we then through that we are getting the power at this point. Along with that, we have one more controller, that is a engine control unit. ECU. So that will control the engine. And now this ECU as well as will have the master control unit here. Sorry, we have the master control unit, and this master control unit will connect with this ECU unit also. That will connect with the motor, this complete this unit also. And then finally it generates an appropriate command for for the whether the power will be taken from the engine or whether the power will be taken from the motor, and when it is motor, whether the power will be taken from battery supercapacitor. That command will be first generated by the master control unit, and then accordingly the individual control unit of the each compartment of vehicle will be operated to drive your vehicle. Now how, what way we approach it? So the dynamic approach will be based on two methodology, backward and forward methodology. So based on the energy flow direction in powertrain of vehicle, two main modeling methods are there to build a vehicle simulation model. So either we go with a backward model, which I have explained you, that is a backward model. So this is known as the effect and cause. Because why it is effect? If we go to the previous slide, the effect is over here. Effect means we are running a vehicle, and the cause is from this source. So we are moving in a reverse directions. We are moving from here, and then finally we are reaching to this point, and that's why it is known as a backward method of propagation. So this is effect and cause method, also called a vehicle to engine power flow method, vehicle to engine and motor power flow method. With an imposed speed cycle, one calculate the force acting on the wheels and process the backward through the drive train up to a primary energy source, which is either fuel or electricity. So the backward facing model works on the assumption that the vehicle follows the speed stress that we have assume a drive cycles, and vehicle is following that speed stress. And this approach also allows the integration of lookup tables, because it is either lookup table or efficiency map, etc., without requiring the actual modeling or physical model of the each and every component of your vehicle system. So backward methods are mostly a higher modularity and are especially characterized by fast software development and much faster simulation runtime, because we assume from the output part, and we regulate in the and we do the regulation in the reverse direction. Other model is a forward method. This is exactly effect, means opposite to the previous one, cause and effect, or engine or motor to wheel method. So we start from engine, we start from the motor. Again, here we'll have the energy storage system also. We start from these, and then we are ending to the wheel. So this is the forward directions. In this method, power flow through the vehicle components start from the engine motor and reaches to the wheel. The forward-facing approach model the power flow in the same direction as the physically power flow through the vehicle. In this method, the vehicle speed is compared with the driver command, and through PI controller, it provides appropriate command to modulate throttle and brake of the motor as well as engine. This will send command to the engine model to generate the required torque, engine as well as motor model to generate a required torque, and then finally the torque command passes to the wheel. So this method uses the measured quality and control signals, and this approach is well suited to the design and development of the for the control strategy of your HEV. The easiest method is a backward method. Now, to once we decide that okay, we would like to move with the backward method, then now the first thing is that what we need is the drive cycle pattern. how to get that drive cycle pattern. We will have different types of drive cycles, which are known as a test vehicle test drive cycles, which usually people are using for the simulations. Or if you want to go with the real time drive cycle measurement, then you can do that measurement also. Nowadays, of course, these things I have executed earlier, so that's why I'm just showing you that how to measure the real-time drive cycles with the help of microcontroller, and that microcontroller will again interface with the NI controller, National Instrumentation Controller, and finally, that what we call it as a lab view. So basically for the measurement, we need to have the wheel tire assembly. Then we have to put the speed sensor. Then you need to have the microcontroller, which will all the time is measuring the speed with which your vehicle is moving. And of course, usually this measurement will take place at 1 second interval, because we know that the dynamics of speed is very slow. So the change in the speed cannot be interpreted in terms of microsecond or millisecond, but the right way is to take the measurement at every 1 second. And then through the serial mode that has been interfaced with the DAQ card, and finally that has been transferred to the PC LabVIEW model. So for that, this assembly has been made, and the you can say the interfacing assembly with the, you can say, a circular ring, and that will be having a number of slots on that disk. This is your circular disk on which the number of slots are there, so that they will be on and off. And accordingly, when this disk will be mounted on the wheel of your vehicle, so as the vehicle is moving, the wheel is moving, the wheel moving will be detected through this disk, and disk will be then after interface with the speed sensor. The speed sensor will sense the crossover of this each and every slots available on disk, and accordingly the speed measurement will take place. And this is nothing but the microcontroller kit which we have used to measure that speed. And this is nothing but the NI instrumentation card. So this is the measured speed. This is for the city drive cycle of the Surat drive cycle. And you can see that of course here we are getting some spikes, so we have to remove this, because we know that in the city you cannot go more than 50 kilometers per hour. Of course, in certain segment for a short period of time, or otherwise usually it is within the range of 40 kilometer per hour, not more than that. Only in a few segments it may have a little bit higher speed, where the traffic may be very, very less. So we have done the measurement on the highway drive cycle also. This is between Surat and Vadodara. And this is express highway drive cycles, that is from Vadodara to Ahmedabad. We've done this measurement. And why we have done this measurement? Because it will reflect the three conditions: the road conditions, then the driver nature, and the third parameter is the traffic. And this part, even though there would not be any traffic, this is showing the nature of driver, that driver may get afraid while taking a turn or something, and that's why the speed pattern will totally change. So basically the drive cycle will always depends on these three parameters, and that's why the nature of operation of vehicle is totally non-linear. You cannot predict directly. But this is just for our analysis, and this we assume that these are the certain drive cycles. Considering all these factors, road conditions, driver natures, and traffic conditions. So now to how to design that vehicle, or you can say how to do the power sharing between the vehicle, and how to design that vehicle with their individual components. We have taken the specification of vehicle, that what should be the mass of that vehicle and all other area, then the mass of the wheel and the wheel radius, etc., efficiency. Then the CD is nothing but drag coefficient, at drag coefficient, and this is nothing but uh, rolling resistance coefficient or the tire coefficient. So as I have told you that the tractive force required to propel the vehicle is aerodynamic, rolling resistance, and this is the acceleration force. Acceleration force usually we define as m into a, but that but as the vehicle is in momentum, it has you can say the rotating element, and that rotating element will have the inertia J, and this inertia J will offer some additional weight. So that additional weight has been considered over here. So this is the, you can say the acceleration is F, or force because of the acceleration is me into a. So me is now the effective mass of the vehicle multiplied by the acceleration with which it is operating. Rolling resistance force will be mass into gravitational force into the uh, fr, that is rolling resistance coefficient, and this fa will be defined as half rho cd a into v square, and the acceleration is m into a, and the third is, you can say, the slope force. But usually this analysis has been done with zero slope or 0 degree of inclination, and that's why that has not been considered over here. So based on this force equations, we have calculated the total force demanded at the wheel, and then that has been converted into the power. Power will be nothing but multiplying it with the velocity, and once we'll get the wheel power, we assume the efficiency model of each and every compartment of the vehicle, and based on that we have determined what should be the rating of each and every component of the vehicle. And for that, I think I have taken the two vehicles, one with 1050 kg, another is 1850 kg, and we are dealing with these two vehicles. So battery rating should be of 20 ampere hour and 12 volt. This is for the design is for the CT drive cycle, as well as you can run it on highway also. This is 500 Faraday with 16 volt. Then the battery capacity for the another vehicle is 40 ampere hour and 500 Faraday per 16 volt. This is one module. So depending on your voltage requirement, you can have the multiple number of modules to be connected in series and parallel to improve the required voltage and current capability. Here the system voltage will be 20 to 40, and the supercapacitor voltage will be selected as 106 volt. So accordingly, how many number of supercapacitor that you have to connect in series, or battery cell you have to connect in series, that can be determined. And then you will have the motor rating, IC rating, that has been calculated. Power electronics rating will be with the peak power rating, and what should be the DC bus voltage, and at what frequency we would like to fire it. So these are, you can say, the ratings of the HV components with different vehicle weights and for a one specific drive cycle. It is not for one specific drive cycles, but it can be averaged, and based on that, this has been considered for this application. Now we have a multiple source. You can say the one multiple source means battery, supercapacitor, and then they drive the motor, and we will have the engine, and then this motor and engine will be connected in parallel to the common shaft, and then they will drive the vehicle. So we have the two propelling source and other two energy storage devices, which needs to be uh, which needs to supply power to motor to a vehicle through motor. So now which, whether the engine will supply power, whether the motor will supply power, whether engine and motor will supply power together, and whether the only battery is supplying power or only supercapacitor is supplying power, or both are supplying power, or whether the engine is operated only in engine mode, or in the hybrid mode, means motor and engine will supply power to the load, or it may be in a power supplied mode plus charging mode. So a different way of can say the power sharing will be there, which basically depends on how your vehicle is driven on a road, and that's why that can be identified through the drive cycle. So now we need to manage the power flow from the individual compartment of vehicle in such a way that there must be a synchronization between the engine, motor, and these two sources, and they will allow you to operate your system or operate your vehicle with its maximum efficiency. So the power and energy, or you can say the energy management system for HEV is must, due to multiple sources available in a single vehicle. So power and energy management system is required to strategize and arbitrate power sharing between the multiple energy sources and the load. So energy itself is simply the time integral of power. So decision in energy management take place at an iteration rate slower than the power management. So we can say energy and power, when we are comparing this is a long-term device, long term, and this is a short term. It is required for short term, this is required for long term. So whichever the level, that means level in terms of energy is required for long term, then definitely their dynamics are slow. Or for a short term, the dynamics are little fast. And once we will find that, okay, the energy related compartment will be related with, as I have told you, that the speed is the one of the factor. Then the SOC of battery, SOC of UC, you cannot predict this, or you cannot predict the variation in terms of microsecond or millisecond, but at least second. These are parameters which has monitored uh, while implementing your energy
ते
management
खाली आहे माझा
system. Hello, hello,
रोल ऑफ
hello.
सॉफ्ट कॉम्प्युटिंग टेक्निक्स फॉर एनर्जी
Can you turn off your speaker? Hello.
हॅलो ठकार मॅडम प्लीज स्पीकर बंद करा.
So the speed SOC of UC, SOC of battery will be a slow dynamics. So they are like a grouped as if it is related with the energy term. The power, that means nothing but how to control, send a control command to the ECU unit of the uh, engine, or send a command to the motor, or send a command to define the power contribution from battery and supercapacitor. So this are in terms of the millisecond. And then finally, once we say that, okay, the engine has to supply power and this much amount of power has to be supplied by engine, then now we have to run this ECU unit, or we have to run the control circuitry. We need to run the control circuitry that is related with the motor and battery and supercapacitor. Or we have to pass on a now command to the DC to DC converter to execute that task. So that third stage will be defined as power electronics management cell. The first cell is energy management cell, which covers these parameters. Power management cell will cover the power sharing, how much amount of power that can be shared by the individual circuitry. And once we know that, okay, this much amount of power we have to take it from engine, this much power we have to take it from the motor, this much power that has to be supplied by supercapacitor battery. So that can be now executed through the power electronic cell. And we all know that the power electronics is operated in microsecond. So the whole power management system will be divided in the three sections: energy management cell, power management cell, and power electronics management cell, based on their time of execution. So as there are several processes involved in the power and energy management system, ranging from long-term decision of energy expenditure to a very high-speed control of power electronics, the modular structures will facilitate each major part of the process to be addressed independently and finally merged to form a complete circuit. So a multi-level hierarchical control system for HEV powertrain is divided into three levels. One, we call it as, basically it is an organization level. If I am comparing it with like a general management system, usually preferred in case of industries or in the commercial offices. So the first level is known as the organization level, and for our vehicle system, it is identified as energy management cell. It is the highest level of this multi-hierarchical control system, and this level has the ability to take decision, judge the vehicle operating mode, that is startup, acceleration, cruise, deceleration, or stationary, in accordance with the vehicle operating information, that is the speed, power demand of vehicle, SOC of energy storage system. And this energy management system then provides a periodic manipulation of set of control parameters to the second level of hierarchical process in order to implement a given strategy and then select the corresponding sub-control strategy in the second level. And the second level is nothing but the coordinated level, or it is a power management cell. All sub-control strategy for different operating modes belongs to the coordination level, which is the middle level of the multi-level hierarchical control system, means that is related to the individual component of the vehicle. So this level coordinates the function of engine, motor, battery, supercapacitor, controller, and resolves the conflict and there. So the power management cell problem is to determine the instantaneous power split ratio between the engine and motor, as well as the power split ratio between battery and engine, supercapacitor, while as regulating the DC bus voltage to the constant level under different modes of operation. I think I'm not tell you about the DC bus, but I will show you here. After this DC to DC converter, we are forming a DC bus. And this DC bus is always operate with constant voltage. And what I have told you, that this energy storage devices will be controlled through DC to DC converter, and the use of this DC to DC converter will facilitate you to use individual source with different voltage level, so that you can control their functionality independently with the help of this DC to DC converter. But this is always, and DC to DC converter will mandatorily maintain this DC bus voltage constant, so that the inverter operations becomes not so complicated as your DC bus voltage is constant. So finally, the last level is a control level, that is a power electronic cell. The engine controller, motor controller, and battery supercapacitor controller now belongs to the control level, which is the lowest level of this multi-level hierarchical control system. This level directly gives the instruction to the engine, motor, and battery supercapacitor and control their operations. So voltage current regulation as well as the system protection take place within this process cell. So we'll have this three hierarchy level of energy management system to control the functionality of HEV with the maximum utilization of each and every source, which is propelling or providing power to the wheel of vehicle. So if we look at the, this can be like in form of triangle. One triangle is this, an actual management triangle, which is related with the management system of any commercial unit, will be always like this. This is the energy management part. This you can say that means this is organization, this is coordination level, and this is the top level, where the decision will finally taken by the higher authority. Here, now to find out their feasibility and all that, many number of people are involved to do that task. And then after this has been passed on to the other level, where they do the further analysis and then scrutinize that whatever suggestions that has been provided by this organization level, consider staff, that can be further modified by this, and then finally the decision will be taken by this. Now in our case, this hierarchical management model will be like a inverted one, because in this particular case this will take high time and this will take low time. So similar way, we'll have our high time will start from here, then the middle time, and then the very high, very low time in which we have to implement this. So it can be interpreted as a top level management, middle level management, and lower level management. So this lower level management is corresponding to power electronics process. Then power management, we call it as the policy, that based on the policy we take the appropriate decision for selection and control of the individual unit of the controller, the vehicle. And the top level is energy management, where the strategy will be formed, that with what strategy you would like to determine the sharing of power between the individual source. And then once that strategy will be determined over here, after that the power management cell will make the policy that which device will share what amount of power. And then after, the power electronics, that is the process, will be implemented. So we'll have, you can say, the concept of modular power and energy management structure. So this is EMS, we call it as a strategy, PMS, policy, and PES, that is process. So organization level provides prescriptions for the actions to be to the coordination level policy, and which in turn generates the feed forward reference power trajectory to the power electronic cell. An output of the power electronic cells are duty cycle command to the power electronics converter, and concisely the energy cell handles the system energy content, power management cell handles the power distributions, and power electronic cell process the system voltage and current. So this way we can manage the power flow from the individual component of the vehicle. So now how to implement that? I have just provided the explanation that this way we can do the management of power flow from individual elements. So now to implement this energy management system strategy for HEV, we need to first know that what are the operating modes of HEV. So we'll have the first mode, usually we call it as electric mode. That means in which, or you can say the only the motor is supplying power, water supply power to the system, to the vehicle, and in that the hybrid energy storage system will come in picture. So due to the multiple storage system, we will have either the UC supply power to the motor or battery will supply power to the motor. This is related with the peak power requirement. So it is a pure electric mode, and in this either the vehicle is operated in upfield or acceleration mode. Then the supercapacitor will supply power. This is when the battery is supplying power, means it is a pure electric mode and running at almost constant speed. That means a normal power requirement of vehicle. Then charging of battery, motor charges battery and motor charges UC. These two things will be under regeneration. When a regenerative will take place, so usually as the regeneration will take place, the power will be absorbed by the UC. If UC SOC is not full, and if UC SOC is full, in that particular case, battery will accept that regenerative energy. So in this case here, the motor is acting as a generator, and this is implemented in two cases. Like I'm just showing you the speed profile. Let's say there is a decrease in the speed, further increase in the speed, and now this is the breakdown conditions. So here we can have the regenerative braking, and in this duration also we have the regenerative braking. This is a deceleration part, not the zero speed part. But higher decelerations will operate. You can operate your motor as a generator, and you can extract the power from the rotating elements. So this way, either the motor will act as a generator and it will charge battery, or it will charge supercapacitor. So everything required some logical steps or some decision making steps, that how to implement that, and that implementation is done through the energy management system with appropriate energy management algorithm. And these are the two other cases, that battery may charge UC or UC may charge battery if both are lagging with their SOC level. So this is rarely happens in the vehicle, unless and until under certain extreme conditions this may take place. So this is known as electric mode operation of your HEV, in which vehicle is operate only with the motor and the energy storage system. Then the second mode is ICE mode. ICE mode will be divided in three parts. ICE will work, only ICE is supplying power to the vehicle, that is a pure ICE mode. Then usually this mode is very much preferred for HEV when the vehicle is driven on highway. So IC will directly, and we know that when the vehicle is running on the road and on basically on highway, the IC engine will work at higher efficiency. So we may operate it with this. And other two modes are IC engine will supply power to the vehicle, as well as it is charging either battery or supercapacitor under certain emergency conditions. So in that case, IC has to generate more power. The first power that is required by the vehicle, and the second power that is needed to charge either this battery or supercapacitor. So this way, IC can operate in these two different mode: charging mode plus charging plus supply mode, and only supply mode. And the last mode is known as a hybrid mode, in which usually the vehicle is running on again highway. And as I have told you that we have the motor and the IC engine, these two are connected in parallel to the common shaft. So usually the IC engine capacity will be low. So if the vehicle is demanding more power, then the motor will assist the engine. So it is known as a power assist mode or a hybrid mode, or it is known as a hybrid mode. So this hybrid mode, the motor and IC engine both are providing power to run the vehicle. So if you look at the power flow diagram, when the only motor mode vehicle is driven by, here I am just putting battery and UC. So power may flow from UC or battery depending on the vehicle operation, the start, that is the acceleration mode, and the normal mode. મારો ક્લાસ ચાલે છે, થોડી વાર રહીને કરું. મારો ક્લાસ ચાલે છે, થોડી વાર રહીને કરું. So here your acceleration mode or a normal mode operations will be governed by these two source, battery and supercapacitor, and the motor will take the power from this and supply power to run the way. Engine only mode, engine is supplying power to run this, and power assist mode, engine and motor both are supplying power. Of course, here you will have the further UC, not only battery, and this will have the UC. This is also UC. So in this case, the power, this is a regenerative mode. Sorry, this is a recharging mode. It means that the engine is supplying power to the vehicle and power to charge the battery. And this is a regenerative mode in which all regenerative energy will be first transferred to the supercapacitor, and the rest may be there then transferred to the battery. So this way, these are the different mode of operations, and based on this mode of operations, the energy management algorithm will be implemented. And as I have told you that the engine will has to operate in its efficient mode, and this is the engine on duration. That means the engine torque and the engine speed must reside in this envelope only. Then only your engine will operate efficiently. So this is again engine off, and on this side also your engine must be off. Why? Because when you operate it above this ring, then definitely the engine will operate with a low efficiency. So this is the region in which you have to operate your engine. And whenever, let's say, your operating point is somewhere over here, right, which is below the torque envelope, then it is always preferable to operate your engine at this point at least. So this additional power will be used to charge the supercapacitor or battery. Or let's say the operating point of your engine is over here, and if additional charge is required, then that additional charge power will be still engine can generate, because it is still operating in the efficient region. So this way the engine envelope has been decided for its efficient operation. So before we implement this energy management strategy, uh, we need to have the certain, we have to do the modeling of the system. That modeling will be done with certain assumptions that the electric power required by vehicle is calculated using only longitudinal dynamics of the vehicle, which I have already explained you. Then the vehicle is designed for both CT and hybrid drive mode. The CT mode, only electrical propulsion is activated, and in the highway mode, and at that time the peak power is delivered by only UC and the average power is delivered by battery. All braking power must be absorbed full first by UC, and if still UC SOC is not sufficient to absorb that, or it is 100%, in that case the battery may uh, accept that charge. But if the regenerated energy is more than the motor maximum power capability, like this is my motor, and let's say the this is the wheel energy, and if when we apply a brake, if this brake energy is more than the rate power rating capability of this motor, which we are operating as a generator, then the complete regenerative braking is not sufficient to stop the vehicle, and in that case we are applying mechanical brake also. Along with electric brake, mechanical brake is used. The launching of vehicle is with 120 km per hour in 18 second time, applicable with the use of pulse power device, that is capacitor, and rest, and which reduces the stress on the battery as well as engine, that is for the highway. And for a city drive cycles, it is I think 50 km per hour, not more than that, has been selected. And we assume that the overall efficiency of electric drive is 80% and it will remain maintained, or we assume that it remain constant throughout the operating range. Urban drive mode is only electric mode. This is what I have already told you. The converter and inverter efficiency will be assumed to be 90%, engine efficiency is assumed to be 34%, and the vehicle will operate in charge depleting mode with a limit of battery SOC should not go below 50%. That means we don't want to operate our vehicle below 50% of the SOC of battery, because it has a two mode, that is two way it can operate. That is, one is only electric mode and then the engine plus motor mode. So when the battery state of charge is low, the engine will provide excess power which will be used by a motor to recharge the battery. That is in a extreme conditions, because probability maybe the engine may not be able to do that. If suppose the vehicle power will be still very low and battery SOC is not sufficient, in that case we have to run the engine even with the lowest capacity. So these are the constraint, that the power, the PUC with that maximum minimum value battery, IC engine and the motor, acceleration rate for urban and the highway drive cycles has been defined, and in terms of the time and the highest speed, and the SOC of UC will not go below 25%, and SOC of battery should not go below 30%, and maximum the 10% will be extra has been for dumping the charge during regeneration, or charging the battery through engine when the engine is not operating in its efficient region. So the basic methodology which I'm just going to explain you is a rule based energy management algorithm. This is also known as a heuristic energy management algorithm. This rule based can be, if you go with an implementation with the AI, then you can go with the fuzzy logic implementation, or you can go with the other AI techniques like I can say the neural network, dynamic uh, programming, energy management algorithm. So different, you can say different types of energy management algorithms are available, even including the sizing process also. Here I have done sizing just by knowing that how much is the maximum power the vehicle is demanding and what is the average power demanded by vehicle. Based on that, the sizing will be carried out. But you can go with the optimization method to be used to size the each and every component of your vehicle along with the energy management algorithm. But many times it is more preferable for a vehicle to execute this algorithm in short period of time, and which requires minimum number of calculations. So usually this rule based algorithm is more preferred for vehicle applications compared to this type of algorithms. Or we have to select uh, can say the AI based algorithm in such a way that they do this execution in short period of time, as well as it is possible with online, sorry, not one, online application. That means when the vehicle is running on a road and you are acquiring the speed data from a vehicle, and based on that, you are implementing this energy management algorithm to share power between the different sources the different component of electric vehicle. So either we have to design AI-based algorithm should be designed in such a way that online implementation of that algorithm is possible. And this rule-based, of course, the rules are framed by uh, the person who is designing this energy management algorithm. So probability may be there. This rule-based theory may not give you the optimal power sharing between the different sources, but at least this methodology is very simple and can be executed very easily. So if you want to anyone who wants to work in this field, they have to definitely start with this. You have to understand the basics related with that, and after that only you can go either with the fuzzy logic implementation, neural network, or any other techniques, AI techniques for power sharing, as well as sizing the system component. So the rules will be like this. Energy management algorithm is based on the prior knowledge of driving pattern. That is first thing. Energy management algorithm will select appropriate energy source based on the power demand of the vehicle as well as SOC level of the electrical source. Power flow through the battery supercapacitor can be controlled based on their SOC level. By the knowledge of current vehicle speed and the desired vehicle speed, the power required will be calculated, and depending on this power requirement, the energy management algorithm will decide whether this power has to be supplied by motor or IC engine or a combination of both. At each instant, the energy management system checks the value of power demand by HEV, their SOC, current levels of battery, supercapacitor, as well as the speed. So it is ensure that the SOC and the current of the battery supercapacitors are within their maximum and minimum limit. And that is especially very important for battery, because we cannot charge and discharge battery at any current. For supercapacitor, it doesn't affect the life of supercapacitor. But if I will charge battery, let's say the battery rating is of 10 ampere hour, and if I will charge my battery at more than 1 C rate, or let's say 2 C rate or 3 C rate, then definitely it will affect the battery life, which is not the case with the supercapacitor. So these are the, can say, the nomenclatures that has been used for P battery, like power of battery maximum, minimum, and all nomenclatures has been used to identify the individual component power level, SOC level, that has been shown with the SOC level, and the maximum power, minimum power with the individual compartment. So it is like PT. Again, we assume that our road is with zero inclination. So this is PR, PG, PA, PAC. Of course, this is with the grade force, and here we are assuming it is to be zero. So it is PR plus PA plus PAC, and this is P auxiliary is the additional power that has been demanded by the all ancillaries available on the vehicle. And the total power will be always P motor plus PICE, and P motor is always defined from the PUC plus P battery. So our first mode of operation is motoring, or you can say the urban city drive cycle. In this also we'll have the two case, whether the speed, I can say, acceleration is either less than zero or acceleration is greater than zero. So when it is greater than zero, it is, you can say, the startup mode, and when acceleration is less than zero, it is a regenerative mode. So accordingly, we may take our appropriate decision, and we may select appropriate device to supply power. So in that, let's say in first case, the acceleration rate is greater than zero, then the total power will be demanded by the motor, with the condition that the battery SOC and UC SOC is sufficient. So the first mode of operation is the acceleration mode, starting, gradient climbing, and high speed operation mode. So in that case, P motor must be greater than zero, And if the P motor required is less than PUC max, that power will be only supplied by PUC. But if the reverse is the case, that the P motor is greater than or equal to PUC max, then the rest of the power will be supplied by the battery. For P motor is greater than 0, but this is a normal operations where the acceleration rate is almost 0, then the P motor will be supplied by P battery. Again, we have to check the SOC level of P battery. Sorry, SOC level of battery. And if suppose the SOC level of battery is not sufficient, and even the SOC of UC is not sufficient, in that particular case, the engine will come in picture. Then engine has to supply power. Of course, this is a very low efficiency mode operation of vehicle. And charging mode, either supercapacitor battery charging through battery supercapacitor and vice versa. But in that particular case, if the battery voltage, battery SOC is greater than 80%, in that case only it will charge the UC, with the condition that the UC SOC should lie between 50% to 80%. And the reverse is also true for the battery. The battery may get some amount of charge from the supercapacitor, or you can say that battery may get charged from the battery, or sorry, engine. That I'm just showing you in the next part. Then you will have the only IC mode. IC engine is powering vehicle only. So in this mode, only IC supply power to the vehicle, and if associated battery will be greater than this, then IC engine will supply power. Then IC engine is powering vehicle and charging battery and supercapacitor. So suppose if the supercapacitor battery will be associated battery will be larger and associated UC will be small, then and if the total power demanded by the vehicle plus the charging power needed to charge any of these source is less than or equal to PIC max, then PIC will be the total power plus the charging power. So in this particular case, the charging power will be used to charge the supercapacitor. And reverse is the case if the associated battery will be less than this minimum. In that particular case, the PT plus P charging will take place with the help of engine. And suppose the battery SOC will be still very, very low. In that case, even if the power demand will be lower, the IC engine has to work. So this has some advantage in the sense HEV will have some advantage in the sense that your vehicle will continuously run even if the charge is not available on battery. That advantage we cannot get if we have electric vehicle and if we do not have charge on battery, only electric vehicle. And then this is you can say the hybrid mode, IC engine motor mode. So if the PIC is less than PT and SOC is still greater than, but as if it is less than this, the IC engine will work. And if additional power is required, because the PT is greater than this, then PT minus PIC max is nothing but the P motor power. And if suppose PT is greater than PIC max, but the SOC of battery will be still lower, then that power has to be supplied by IC engine. And since the battery SOC should not cross the lower limit. So this way we'll have a different, or you can say the different range and different level uh, of the battery SOC, supercapacitor SOC, and accordingly we can implement this energy management algorithm to control the power flow between the individual compartment of this. And this theory is known as a rule-based theory. And in regenerative mode, your PT is less than 0. That means your acceleration is also negative. And if SOC of UC is 100%, and battery is also 100%, mechanical brake will be applied. But if PT is less than 0, but then motor power will be same as PT. It means that the motor is sufficient to provide the regenerative braking. And if SOC of UC is lying within this, motor power is simply delivered to the ultra capacitor to charge it. And if UC get fully charged, and if a battery SOC is less than the minimum value, in that case, P motor because P battery and the battery get charged through regenerative braking. But usually we never prefer these mode of operation because it may affect the battery operation. And these are the whatever the rules which I have already told you in the previous case, in the previous slides, that has been made in form of the flow chart. So we start with the driving cycle, then we find that what type of driving cycle it is, that is speed is less than or greater than 50%, sorry, 50 mileage per hour, 50 kilometer per hour. Accordingly, it can be either urban or highway drive cycles, and accordingly the decision will be taken. Similar way, this is a highway flow chart, and this is a flow chart for the regenerative braking. Whatever rules I have already explained you, that has been framed in form of this flow chart. And then this is a complete simulation model in the, I can say, in MATLAB. This is the drive cycle data. This is our Indian drive cycles test. Indian drive cycle. Indian test drive cycle, which is available on NET. We have used these and we have done, see, this is nothing but the energy management system, or the energy management system will be designed in this block. And we have used a rule-based theory to implement this power sharing between the individual source of a vehicle. And this is supercapacitor, this is battery, this is motor, and this is engine. And accordingly, the power sharing will take place. And finally, this has been supplied to the vehicle. So you can see here the result, that this is my drive cycle, and this is urban drive cycles, and you can see that the UC is providing the maximum power while the battery is providing very small amount of power. Even you can see that the battery current get completely controlled while supercapacitor current is very, very high. Similar way for the highway drive cycles, these are the crafted highway drive cycle, that we assume that okay, initially we are having a sharp acceleration, then after some time again we have another acceleration, and then after your vehicle is running on constant speed, and then we are simply at this higher speed we are implementing a regenerative braking. So in this particular case, you can see that the blue is the supercapacitor is providing power for this period. And then after the green power is nothing but the IC power, so IC is supplying power. And this is the red line, that is a battery power, and maybe it may charge the supercapacitor here. Similar way, you can see that the battery SOC will be very less varying, but the SOC of UC will be varying with a very high value, and all regenerations will be absorbed by this UC. Similar way, in case of the highway drive cycles, you can observe over here is this, the sharing of the power, and this is the SOC of supercapacitor and SOC of battery, because they are used only for a short period of time, and then after the whole power will be supplied by engine. Oh, sorry. Okay. And this is with the, you can see the SOC of battery in this way, SOC of supercapacitor, the power, etc. The same simulation, same methodology is used to simulate the same vehicle with respect to Indian drive cycle. So that measured Indian drive cycles, which I have shown you. So first drive cycle is a Surat City drive cycle number 2. And that can be, this is its speed profile, and from that, how much amount of the power that will be energy can be drawn from battery, and this is from supercapacitor, this is from battery, and these are the SOC variation of supercapacitor and battery. You can see that the supercapacitor can get charged and get discharged, and it is working well within the limit of 25% SOC, and battery is not going above that. So this is the energy regenerated. There is no energy regeneration in battery, but energy regeneration will take place with the UC, that again it satisfied our requirement. The SOC variation of battery, that means if the power will be supplied only by battery, then this is the SOC of battery. You can see that the SOC of battery will greatly reduce. It is almost moving towards the 50% range of the SOC. And this is the, you can say, the power, the energy utilized by the battery and energy dumped in the battery. And this is the, if it is simply operated with the engine, then this will be defined in terms of the fuel consumption of our engine. So we have operated it with the same drive cycles, with either only engine or only battery, or battery and supercapacitor. This is an urban drive cycle. So usually the power sharing is not there between the motor and engine. Similar way, this is the profile for ICDC3, a little bit more sharp speed variation profile. And this is nothing but the SOC and the UC, that is a combined source. We are getting this variation. You can see that again the supercapacitor is not going below 25%. Energy in the UC and battery is of this form, and the energy regenerated, that is shown in the supercapacitor here, and this is for the battery. And this is with the alone battery. You can see it is now moving towards the range of 0.55 or even less. And these are the power and the energy consumed and energy absorbed under regeneration. And this is if I'm running the same vehicle only with the engine, then this is the fuel consumptions. Now, based on this, the calculation has been made that for IDC 2 and 3, if I am having a battery supercapacitor combination, then the battery will consume 800 power, or the battery rating should be related with the 800 watt, and the UC with 2000 watt. And if it is alone battery, it is 2800 watt rating battery I need to use. And if it is only engine, in terms of the engine, you can say the 980, and for the IDC3 it is 1350, that is in terms of the gram. And energy regenerated when it is a combination battery plus UC, 690 will be generated, and 1050 will be generated in the second case. But only with the battery, 600 and 900 will be generated. And if you look at the fuel cost, when it is only driven by the engine for 14 kilometer and 17 kilometers, 96.46, and this is 132.98. If it is only driven by engine, then the cost will be 24.4, and for second cycle it is this. And if it is only it is run by battery plus supercapacitor, then the energy charges is of 23 rupees and 27.5 rupees. So this way you can see that when we are operating it only with battery or battery plus supercapacitor, the performance of the vehicle will greatly increased. And if you will look, I think the same thing I already shown you over here. This is the same thing what is there. Then the simulation results with the hybrid drive cycle. And for these hybrid drive cycles, you can see that the certain contribution is from the battery, and this is from a battery, this is from a supercapacitor. But still, the supercapacitor SOC has not been reduced drastically, because now this is a hybrid drive cycle, so part of the power will be supplied by the engine. And you can see that here the engine may get turned on depending on your requirement. And for IHDC1, the energy utilized from the battery supercapacitor is like this, and energy regenerated is like this. And you can see here when the supercapacitor has reached to the 0.5%, then we don't want to operate it below that. And that's why you can see here that the battery has accepted that charge. And this is the fuel consumptions. This maximum is 4500 grams has been used. Similar way, we have done the simulations for IDC1 and IDC2, and these are the final results, that how much amount of energy that has been returned, how much amount of energy that is available in the stored in the rotating elements. Each rotating element will have their own inertia, so certain amount of energy will be there. And finally, the IDC2, when it is operated as per the rules framed by us, will operate at highest efficiency. Of course, here in the highway, with a very high speed, as the engine is operated with very low efficiency. Hello, madam.
Yes, madam.
So I think now time is up, so I cannot explain them about the fuzzy logic part.
Yes,
Uh,
yes. Okay,
right?
ma'am.
I'm just terminating my class here, right?
Yes, madam.
So our conclusion is that if we will have the proper energy management system and their proper energy management algorithm, we are able to operate our vehicle at its highest efficiency, and each and every source available in a vehicle will operate with their maximum efficiency, and that's why the overall losses in the system will greatly reduce. But of course, we'll have so many other different rules. You can use that rules, and you can further improve the power sharing and the overall efficiency of vehicle by appropriate or optimize the power sharing between the individual component of your source component of your vehicle. Thank you so much.
Thank you, ma'am.
Okay.
Participants, do you have any questions? Ma'am, can I ask the question?
Yes, you can.
Ma'am, do you have you validate this Simulink model with the hardware results?
Yeah, that has been validated with a very on a very small scale level, laboratory
Okay.
level, with
Okay.
battery, supercapacitor, and we have used brushless DC motor, inverter, two separate converter, and then we have implemented this energy management algorithm.
Okay, ma'am.
But that result I have not shown here.
Okay. And all this rule-based theory is based on a fuzzy logic.
We can now frame it in the fuzzy logic also. The rest part of my, because say if I will directly start with the fuzzy logic, no one can understand how to implement or
Hmm.
how to design energy management system and their algorithm to control the power flow from the individual element.
Yes.
So now they can use the say rule-based theory and fuzzy logic theory are almost similar. But
Yes.
the difference is that I will just show you with a few this uh, this multiple number of fuzzy sets we can set with the in terms of either with I can define it with the acceleration level, or I can define with the current level whether the system is demanding high current, low current, medium current, and based on that we have done the energy management system implementation with fuzzy logic for battery supercapacitor, as well as we have done it for the motor and engine also. But that engine, with the engine part, we have done it only simulation. not real-time implementation, but this hybrid energy storage system implementation has been done in real time also. And this modified rule-based theory, that is fuzzy logic-based theory, has been again implemented by my student, but he is doing his PhD, so I cannot disclose that thing. That's not shown in this PPT.
Okay, thank you, ma'am. Ma'am, please, can you share with us your contact details?
Yeah, shall I write down here somewhere?
Yes, in the chat box, you
Or
can.
can I write on the screen? Is it
Yes,
visible to you? Okay.
yes, ma'am.
9426746336. This is my contact number. Hello.
Yes, ma'am.
And it is available on net also. I have placed my mobile number on net also.
Yes, ma'am.
That is our website.
Okay.
IT website. You can get all information.
Yes. Thank you very much, ma'am, for nice and wonderful session conducted by you. Ma'am has covered energy storage system for vehicle application, also ultra capacitor and its working principle. Ma'am has also explained battery and ultra capacitor hybridization. Then ma'am has covered electric vehicle and its infrastructure. Ma'am has covered energy management system for electric vehicle, hybrid electric vehicle. Then rule-based algorithm for a energy management system in hybrid electric vehicle. Ma'am has explained the hybrid electric vehicle Simulink model and its implementation in the MATLAB very well. Thank you, ma'am. Definitely, it will help us for our research application or research study in the future. Um, thank you,
Uh,
ma'am.
can I add one point? Those who wants to work in the field of electrical vehicle, either purely on the electric vehicle or on the charging sides, lots of scope is there, and still the improvement in the system performance is very much required to have acceptance of this electrical vehicle by the consumer. And as far as the India is concerned, we have if you look at our population and the population of vehicle, it is very very large compared to the other countries. So we have tremendous scope to do research in the field of EV, HEV, or on a charging of uh, vehicle storage system. Thank you
Yes,
so
ma'am. Thank you, ma'am.
much.
We will end our session over here. We will start with our next session
Okay, so
within
I'm
5 minutes.
okay. Thank you
Thank
so
you,
much
ma'am.
for giving this opportunity to